I want you to imagine digging up a digital time capsule.
Oh, man. Yeah. Like a real software archaeology dig.
Exactly.
Huh.
We are talking about a piece of software from 1998, written in raw C, and its entire purpose was just to visualize music.
Right back when you'd fire up your Beige Tower PC, right?
Yeah, the beige tower, the clunky, glowing CRT monitor. You'd load up a MIDI file and just watch this program turn digital notes into these like cascading colors and
It
shapes.
was basically magic at the time.
It really was. And today, we're actually looking at the original source code for that artifact.
It's fascinating.
It is. And the question we're exploring in this deep dive is, well, if we took that foundational idea, untangled all that legacy code, and rebuilt it using the absolute cutting edge of software engineering today.
Right, like stepping through Java and then descending into GPU accelerated Rust.
Exactly. And finally, wiring the whole thing up to deep learning neural networks. Like, how far could we push it?
It is a massive software engineering journey. I mean, we are tracing the evolution of a single concept across, what, 3 decades of computing paradigms?
Good, good, yeah.
We go from a developer literally fighting against the raw constraints of 16-bit memory management.
Oh, the 16-bit days.
Right. And agonizingly slow CPU rendering, all the way to modern compute shaders processing tens of thousands of visual entities in parallel.
So if you've ever played around with legacy systems or, if you're just fascinated by how a simple, elegant idea can scale into the future, you are going to love this deep dive.
It's going to be a wild ride.
Definitely. So we have this really fascinating stack of original materials driving our conversation today. We're looking at a literal 1998 source code file. It's named allcode.txt.
Great naming convention, by the way.
Very straight to the point. It's for a program called the Midi Monitor DLL for Powertracks Pro. And we're looking at that alongside a massive architectural teardown, a file called Claude Midmon 22.txt, which is basically a blueprint on how to modernize it.
Yeah, it's a full modernization breakdown.
So let's put ourselves back in 1998 for a second. The original developer, this guy named Eric Rangel, he was building something that was computationally very expensive for the era.
Insanely expensive.
Right. Visualizing real-time musical data while a sequencer was simultaneously trying to play the audio.
Which, I mean, that was no small feat on a Pentium processor, let's be real.
Kidding.
In 1998, MIDI, the musical instrument digital interface, it was the undisputed lifeblood of digital music. And people forget MIDI isn't audio.
Right, it's not a waveform.
Exactly. It's sheet music for computers. It tells the synthesizer what note to play, how hard to hit it, and exactly when to let go.
So Eric built this dynamic link library, right? A DLL.
Yeah, DLL that hooked directly into a popular sequencing program at the time called Powertracks Pro Audio.
Gotcha. So the user would load their song, hit play, and then they'd have to physically hit Alt-Tab on their keyboard to switch over to the visualizer.
Yeah, to this full screen 640 by 480 VGA graphical display of their music.
And the structural logic of that 640 by 480 screen, that's what really catches my eye when looking at this.
It was very structured.
Yeah, he divided the display into 16 vertical columns. Because, well, anyone who has messed around with older synthesizers knows standard MIDI operates over 16 independent channels.
Right.
So as the music plays, the notes appear as these little rectangles or bars falling inside these specific channel columns.
And the mapping was strictly logical. The vertical position of the rectangle represented the pitch.
Oh, okay.
So your low bass notes were near the bottom of the screen, and the high synth leads were near the top.
Makes sense.
And then the length of the bar represented the note's velocity, like how aggressively the key was physically struck by the performer.
Wow. So it's actually capturing the human element there.
Exactly. And the color of the bar was tied to the instrument family. Plus, at the bottom of each column, he engineered these small horizontal indicators to track pitch bends.
Oh, that's clever.
Yeah, and along the right edge of the screen, he had these little controller boxes tracking continuous data, like volume levels and sustain pedals.
That is just an incredibly dense amount of information to push to a screen in 1998.
It really was.
So how did the DLL actually talk to the main sequencer to get all that data? Because looking at the raw C code, it clearly didn't use modern event listeners.
Oh, no, not at all.
It relied heavily on this polling mechanism, right? He used a Windows OS function called setTimer to create this really rigid 50 millisecond loop.
Yeah, polling was pretty much the standard paradigm back then. Every 50 milliseconds, regardless of what else the computer was doing, that timer would just fire.
Like clockwork.
Exactly. The DLL's code would execute and immediately call a function to invalidate the application window.
Invalidate. What does that mean in this context?
So in the Win32 API, invalidating a rectangle of the screen basically puts a WMA18 message into the application's message queue.
Okay.
It's the program's way of telling the Windows OS, hey, this visual area is stale, please redraw it right now.
I'm trying to picture the efficiency of that. It feels like a frantic chef.
A frantic chef.
Yeah, like a chef repeatedly opening the oven every 5 seconds to check if the food is done, rather than just waiting for an oven timer to beep.
That is a brilliant way to put it.
Or like sitting at a desk, hitting the refresh button on a dial-up web browser every single second, hoping a new image line has loaded.
Yes. Instead of the browser just notifying you when the download is finished, you are actively burning your own CPU energy, constantly asking, are we updated yet? Are we updated yet?
Exactly.
That is the inherent flaw of polling, but back then it was a necessary evil.
Right.
So during that paint cycle, the program had to figure out what MIDI events had actually occurred since the last refresh. And to do this, it read from a circular ring buffer.
Okay, break down the ring buffer for us.
So a ring buffer is a fixed size array in memory. It has a head pointer where new data is written and a tail pointer where the data is read from.
Makes sense.
And when either pointer reaches the end of the array, it just loops back around to the beginning, to index 0.
Okay, but the code here strictly caps that buffer at 1,000 events. If the MIDI head catches up to the MIDI event tail, it just forcefully wraps around.
Yep.
To a modern developer, someone who might allocate arrays with literally millions of elements without thinking twice.
Oh, easily.
Yeah, a 1,000 event limit seems almost quaint. Why was he so aggressively constraining the queue?
It comes down to the absolute terror of the 16-bit segmented memory model that Windows 95 and Windows 98 were built on top of.
The terror?
Oh, absolutely. Allocating massive contiguous blocks of global memory in that era was basically playing with fire.
Really?
Yeah. If your pointers drifted even slightly outside your designated memory segment, you didn't just crash a program.
What happened?
You triggered a general protection fault to GPF and you brought down the entire operating system. Blue screen of death.
Oh, wow. So you take down the whole ship.
Precisely. And the developer's release notes actually mentioned that an earlier version of this DLL caused GPFs for users because the memory allocation wasn't tight enough.
That's wild.
So limiting the queue to exactly 1,000 events was just a survival tactic. It was the only way to ensure the application remains stable.
It's so fascinating how those hardcore hardware limitations dictate the actual software design. You see this heavily in the configuration logic, too.
Oh, INI file.
Yeah. He used an INI file named midmorin, minorc-ini, to parse the general MIDI patch banks and map them to specific RGB color values.
Right, because otherwise it would just be chaos.
Exactly.
Yeah.
Pianos were mapped to red, bass instruments were purple, synth leads were dark green. It really feels like a way to bring immediate visual order to what could otherwise just be a screen full of flashing rectangles.
It was a vital piece of user experience design, but I'll tell you, the real ingenuity in dealing with 1998 hardware limitations shows up in the text note mode.
Oh, I love this part of the code.
It's so clever. If a user didn't want the graphical bars, they could toggle a mode to see the actual musical letters like C, D, E, flat, literally scrolling up the channels.
Right. And he didn't use standard Windows fonts for this.
Nope.
He didn't just ask the operating system to draw an Arial or Times New Roman C. He wrote a completely custom function called drawchar.
Hand-coded.
Yeah. He literally hand-coded the pixel coordinates for a 5x7 font matrix. He used raw move-to and line-to commands to draw the letters line by line.
And there's a very specific reason for that. Windows GDI, the graphics device interface, was notoriously inefficient at rendering TrueType fonts rapidly.
Really? I always thought text was lightweight.
Not TrueType text. Font rendering involves really complex vector math, anti-aliasing calculations, memory mapping.
Oh, I see.
If Eric had asked the OS to render dozens of rapidly changing TrueType letters every 50 milliseconds, the CPU would have completely bottlenecked.
Just from drawing letters.
Yeah. The frame rate of the visualizer would have dropped to single digits. And worse, because of how Windows worked, it might have interrupted the audio sequencer itself, causing the actual music to stutter.
Wow. So bypassing the OS text engine entirely to draw raw pixel lines was just a brute force, brilliant optimization.
Absolutely.
But, okay, the defining visual feature of this 1998 artifact, the thing that actually made it look futuristic to users back then, was the fade system.
Oh, the history trails.
Yes, when a note stopped playing, the visual rectangle didn't just instantly vanish from the screen, it left a history trail. It faded out over time.
And I cannot stress enough, implementing that on a CPU in 1998 was a monumental task.
I bet.
The code reveals this system that faded notes through 5 configurable phases, right? Changing the color and the width of the rectangle as the acoustic energy supposedly decayed.
Right, so it looked like it was fading away.
Yeah, and to achieve this, the DLL had to maintain massive state arrays. Stuff like fade counter, fade left, fade right, fade accord, and fade phase.
And he capped this system at a maximum of 500 concurrent fade events, right?
Exactly.
Let's walk through the math of why 500 was the absolute ceiling here.
Okay, let's do it.
Because every 50 milliseconds, the timer fires. The CPU has to manually iterate through that array of 500 fading notes.
Yep.
For every single one, it has to update the phase logic, calculate new coordinates, ask the operating system to create a new colored brush, and then issue a fillrect command over the system bus to the graphics card.
So if you do the math, that is 500 fillrect calls 20 times a second.
Wow.
That's 10,000 drawing commands a second, handled entirely sequentially by a single core CPU that is also, by the way, trying to manage the operating system and play a MIDI file.
It was pushing the desktop architecture of the 90s to its absolute breaking point.
Literally to the edge.
So we have this incredible, highly optimized monolith of a C program. It's that single 50-millisecond loop, frantically checking the oven, reading a small ring buffer, and manually painting hundreds of rectangles. But if our goal is to modernize this, like to eventually reach tens of thousands of visual entities running at 60 frames per second on a modern 4K monitor, this architecture is a dead end.
Completely. You can't scale it.
We have to fundamentally untangle the logic. So let's talk about the modernization blueprint from the architecture document.
Right. So the original code is what software engineers call tightly coupled.
Tightly coupled, meaning what exactly?
It means the input mechanism, the data processing, and the screen rendering are all braided together into one unstoppable loop. In modern engineering, we decouple those concerns. We use a strict 3-layer architecture. We break the system into an input layer, a state layer, and a render layer.
I like to think of this decoupling kind of like standardizing global shipping containers.
Oh, I like that analogy.
Yeah, so before shipping containers, a dock worker had to know exactly what was in every sack and barrel to figure out how to pack it onto a ship.
Right.
It was slow, and it was tightly coupled to the cargo itself. But once we standardized the steel container, the crane operator doesn't need to know or care if the box holds electronics or bananas.
The crane just moves the box.
Exactly. The crane just moves the box, the ship just holds the box, or, it's like a 3-tier cake. If you want to swap out the frosting, the graphics API, you shouldn't have to bake a whole new base layer for the MIDI input.
That is a highly accurate way to look at it. So in that analogy, the input layer becomes our cargo packer.
Right.
In a modern architecture, we abandon polling entirely. No more frantic checking. The input layer relies on asynchronous event listeners.
Okay, so it just waits.
It sits quietly in the background, consuming almost zero CPU. When the OS's MIDI driver receives a message from a keyboard, it fires an interrupt.
And then
The input layer catches that message, wraps it up into a standardized container, and pushes it onto a thread-safe queue.
so it's no longer repeatedly asking if there's new data. It's just waiting for a tap on the shoulder.
Precisely. Then we have the middle layer, the state layer.
The data model. Exactly. The state layer is pure data modeling. It represents the virtual world of our visualizer.
What does it actually do with the containers?
It pulls those standardized containers off the queue and updates its internal ledger. It changes the status of a note from off to on. It updates the countdown timers for the fading trails, and it calculates the colors.
This doesn't draw anything, right?
Crucial distinction. Zero rendering happens in the state layer. It is completely blind to monitors, pixels, or graphics APIs. It is literally just math in memory.
Which leaves the render layer, our crane operator in this analogy.
Right. The render layer runs on its own independent loop, locked to the vsync of the user's monitor, typically 60 or 120 times a second.
VSync being the refresh rate of the screen.
Yep. When it's time to draw a frame, the render layer takes a rapid snapshot of the state layer's ledger, figures out where the rectangles should be, and paints them to the screen.
And because these systems are decoupled, the render layer doesn't care if the MIDI data arrived a millisecond ago or a week ago, right? It doesn't care at all. It just draws the current state.
This means if we want to rip out the entire graphics engine and replace it with something infinitely more powerful, we don't have to touch the MIDI parsing logic at all.
Exactly. Which brings us to the first phase of the modernization blueprint.
A stepping stone.
Right, because moving from 1998C straight into modern GPU computing is a massive leap.
Too many variables changing at once.
Yeah, it introduces too much risk. So the architectural teardown recommends using Java as an intermediate stepping stone to validate this decoupled three-layer design.
I can see the logic there. Java provides an incredibly robust standard library out of the box, specifically the javax.sound.midi package.
It's fantastic for this.
You don't have to write custom C++ wrappers to talk to the Windows WinMM API or the Mac Core MIDI framework. Java basically abstracts all of that hardware-level complexity away.
Yeah, it's so clean.
Right.
You simply ask the Java MIDI system class for an array of available devices. You open a transmitter on your chosen device, and you attach a receiver. When a MIDI message hits the actual hardware, the receiver.send method is triggered automatically.
And because we need to safely pass that data to the visual side without crashing, Java gives us thread-safe data structures right out of the box.
That's the beauty of it.
The receiver.send method is running on a background thread managed by the Java virtual machine, and it takes the MIDI data and drops it into a concurrent linked queue.
And we have to talk about that specific data structure because it is vital here.
The concurrent linked queue.
Yes. A concurrent linked queue in Java is lock-free. It uses low-level atomic variables to ensure that even if the MIDI thread is writing data at the exact same microsecond that the graphics thread is trying to read data, neither thread blocks the other.
Oh, wow.
Yeah. And more importantly, the data doesn't get corrupted. You completely avoid the race conditions that would otherwise cause the program to crash.
Then for the graphics side, the blueprint suggests using Java's Swing toolkit and the Java 2D API.
Right. It's basically an object-oriented evolution of the old Windows GDI logic.
So instead of managing raw OS brushes like in C, you just override a pin component method and use graphics2d.fillrect.
Exactly. And Java solves our old 50-millisecond timer problem so elegantly through the event dispatch thread, or the EDT.
Ah, the EDT. How does that work?
In Swing, all UI updates must happen on this single specialized thread. So we set up a Swing timer to fire every 16 milliseconds.
Which gives us a smooth 60 frames per second.
Bingo. When the timer fires on the EDT, it drains the concurrent linked queue, updates our skate layer, and calls repaint.
Now, I have to play devil's advocate here.
Go for it.
The common hesitation with building desktop applications in Java, at least historically, has always been distribution.
Oh, sure. Users hate installing Java.
Exactly. In the past, you had to ask your end user to go download a Java runtime environment, deal with updater prompts, navigate those annoying security warnings. It was a massive point of friction. Isn't Java considered kind of old school for graphics?
It used to be a headache, I'll give you that, but modern Java has completely eliminated that friction.
Really? How so?
Since Java 14, the JDK includes a packaging tool called JPackage.
Package.
Yeah. You don't ask users to install Java anymore. JPackage takes your compiled code, analyzes it to see exactly which parts of the Java runtime it actually needs, strips out everything else, and bundles it all together into a native installer.
So the user doesn't even know it's Java.
Exactly. You get a standalone .exe for Windows, a .dmg for Mac, or a .deb for Linux. The end user double-clicks it and installs it like any other normal piece of software. They are completely insulated from the JVM running underneath.
Okay, that's huge.
And as for the old-school graphics argument, for drawing 2D rectangles without shaders, Java's software rendering fallback is actually incredibly robust. It's the most pragmatic intermediate step.
It's a perfect architectural bridge. We validate the data separation, we get a clean 60 feet render, and we prove the concept.
Exactly.
But, and this is a big but, Java 2D, even with its automatic hardware acceleration, is fundamentally built for drawing basic shapes.
Right, it has its limits.
If we want to move beyond 500 rectangles, if we want to push 10,000 shimmering, dynamically fading note trails on a 4K display.
The CPU overhead of Java 2D will eventually just choke and hit a wall.
Right. So to achieve true parallel processing, we have to descend to the metal. We have to move to Rust.
Rust is the ultimate destination for this kind of high-performance tooling.
Why Rust specifically?
It gives you the raw speed of C++A, but with a compiler that mathematically guarantees memory safety.
That's the borrow checker. Right.
Yes, the famous borrow checker. It ensures that the kind of memory leaks and general protection faults that haunted our 1998 developer are physically impossible to compile. The compiler literally won't let you build the program if it's unsafe.
That is incredible peace of mind. So the modern stack outline for this final destination phase is pretty aggressive.
Very aggressive.
For the MIDI input, we bypass the JVM entirely and use a native Rust crate called Midier, which talks directly to the OS drivers with basically zero overhead.
Yeah.
We use a library called Winit to handle cross-platform window creation, but the true engine of this modernization, the real powerhouse, is the graphics backbone, a framework called WGPU.
WGPU is a revelation in graphics programming. I cannot overstate this.
Break it down for us.
It is a cross-platform API written entirely in Rust, and it serves as a native implementation of the WebGPU standard.
Now, when most people hear WebGPU, they think of browser-based games, right?
That is its origin, yeah. But WGPU brings that standardized architecture to desktop applications. It acts as an abstraction layer over the completely chaotic landscape of modern graphics APIs.
Chaotic is a good word for it.
It really is. WGPU sits on top of Vulkan on Linux systems, Metal on Apple hardware, and DirectX 12 on Windows. So you write your graphics logic once in Rust, and WGPU translates it into the optimal calls for the user's specific graphics card.
But the initialization process for WGPU is intensely explicit compared to Java, isn't it? Like, you don't just ask for a canvas to draw on.
Oh no, it makes you work for it. You start by creating an instance, which is your entry point to the API.
Okay, an instance.
Then you ask the instance to find an adapter, and the adapter represents the physical graphics card plugged into the motherboard.
Right.
From the adapter, you request a device and a queue.
And what do those do?
The device is your logical connection to the GPU. You use it to allocate memory buffers and create rendering pipelines. And the queue is the command channel. It's how you actually submit work for the GPU to execute.
Wow, so you're really managing the plumbing here.
Oh, yeah. And finally, you configure a surface, which is the bridge between the GPU's memory and the physical window displayed on the monitor. It forces the developer to understand exactly how memory is being laid out and transferred.
And that explicit control is how we solve the 500 fading notes bottleneck, isn't it?
That's exactly how.
Because in C and Java, the CPU is running a loop. It looks at fade number 1, does the math, updates the color, looks at fade number 2, does the math.
Completely sequential.
Right. But in Rust, we abandon CPU loops for visual state updates entirely. We use something called a compute shader.
This is the paradigm shift of modern GPU programming. A graphics card is fundamentally different from a CPU.
How so?
Your CPU might have, 8 or 16 incredibly fast, complex cores designed to handle highly unpredictable tasks.
Right, running the OS, running a browser.
Exactly. But a GPU has thousands of relatively simple cores, and they are designed to do the exact same mathematical operation at the exact same time.
So it's like an army.
Yes. So we take all of our fade data, the X and Y coordinates, the color values, the decay phases for all 10,000 potential history trails, and we load that massive array into a GPU storage buffer.
And then?
We then write a tiny program using WGSL, that's the Web GPU shading language.
What does that tiny program actually do?
Well, a compute shader doesn't draw anything, it just crunches numbers.
Yeah.
When we dispatch that compute shader, we tell the GPU to assign one of its thousands of cores to each individual fading note in the buffer. Simultaneously. Core number 1 calculates the math for note 1. Core number 8000 calculates the math for note 8000. They all execute at the exact same time in parallel.
So what took the 1998 CPU 50 milliseconds of agonizing sequential work is completed by the GPU in, what, a fraction of a microsecond?
Literally a fraction of a microsecond.
That is just mind-blowing.
Yeah.
But once the math is updated in that buffer, how do we actually get it on the screen? We obviously don't want to issue 10,000 separate draw commands.
No, that would ruin all our performance gains. We use a technique called instanced rendering.
Instance rendering. Okay, explain that.
Instead of telling the graphics card to draw a rectangle and then telling it to draw another rectangle, we upload the geometry of a single rectangle to the GPU memory just once.
Just a template.
Exactly, a master template. Then we issue a single draw call. We instruct the GPU pipeline. Here is the master template for a rectangle. Now look at that storage buffer we just updated with the compute shader and draw 10,000 instances of this template, applying the specific coordinates and colors from the buffer to each one.
That is a staggering reduction in overhead. I mean, it's like CPU rendering is a single, incredibly fast painter running around a huge canvas, sweating to get it all done.
Yeah.
And GPU rendering is an army of 10,000 tiny painters who each just step up and paint exactly one rectangle at the exact same millisecond.
I love that analogy. That's perfectly stated. It fundamentally breaks the performance ceiling.
But here's the fascinating thing. Now that we have this immense computational power, this army of GPU cores just waiting for instructions, we realize we're actually starving it.
You're starving it.
Because if we only feed this system basic MIDI node on and node off commands, we are ignoring a massive layer of musical expression.
Absolutely. The 1998 program mapped pitch and velocity, which is fine, but a synthesizer performance is rarely that static. Musicians manipulate the sound constantly while a note is playing.
Right, and this data is transmitted through control change messages, or MIDI CC data.
Yeah. The MIDI 1.0 specification allows for 128 continuous controllers.
So these are essentially digital knobs and sliders that send values from 0 to 127.
Right. Exactly. And if we extract that data, we can turn this visualizer from a static grid into an organic, breathing reflection of the actual human performance.
Let's look at the specific enhancements detailed in the architectural teardown for this, because they are incredible. The most transformative one is CC64.
The sustain pedal.
The sustain pedal, right. In the original program, the moment a musician's finger lifted off a key, the note-off event triggered the fade trail. The visual rectangle just began to die immediately.
But if a pianist has their foot pressed on the sustain pedal, the physical dampers inside a real piano are lifted. The string is still vibrating.
The acoustic reality is that the note is still playing at full volume.
Exactly. So with our decoupled state layer, we can constantly monitor the value of CC64. When the pedal is depressed, we intercept the note-off messages.
So the visual rectangles don't fade.
No, they hold their full brightness on the screen, exactly mirroring the acoustic sustain.
And when the musician finally lifts their foot,
when the CC64 value drops to 0, the state layer releases all those held notes simultaneously. It creates this incredible cascading visual decay down the columns.
that is so cool. It creates visual truth.
Visual truth, yes.
We can apply similar logic to CC11. Expression.
Oh, expression is huge.
Expression is typically used for dynamic shaping within a phrase, right? Like a violinist swelling the volume of a sustained note or a brass section performing a crescendo.
Right, so instead of our history trails decaying at a fixed linear rate based purely on time,
Like a static timer.
yeah, instead of that, we can map their brightness dynamically to the CC11 data. A loud, aggressive note fades slowly from a blinding peak, while a soft note decays rapidly into the background.
And then we have the mod wheel, which is CC1. Synthesizer players constantly ride the mod wheel to inject vibrato into a lead line.
Constant manipulation.
So the architecture suggests mapping the CC1 value to a shader parameter that controls the physical width of the history trail.
That's my favorite one. As the musician pushes the mod wheel up and the pitch begins to waver, the visual bar literally begins to shimmer and pulse horizontally on the screen, matching the exact frequency of the vibrato.
It's like you can see the sound wave wobbling.
Yeah.
And if we expand our thinking to the spatial mix, we look at CC10, which controls pan, the placement of the sound between the left and right speakers.
Right, because in the 1998 paradigm, the visual bars were strictly locked to the dead center of their designated channel column. There was no left or right.
But if we feed the pan data into our compute shader, the fading trails can physically drift left or right within their vertical boundaries.
Yeah.
So if you have a string section that is panned hard left in the audio mix, you will see its visual history trails constantly drifting toward the left edge of the screen. You are generating a visual map of the stereo field over time.
It's incredible. And the mapping can get even more abstract than that.
Like what?
Consider CC74, filter cutoff.
Oh, filter cutoff.
Yeah, on a synthesizer, opening the low-pass filter allows the high frequencies to escape, making the sound harsh, bright, and aggressive.
And closing it traps those frequencies, making the sound muffled, dark, and warm.
Exactly. So the proposal maps the filter cutoff value to the color temperature of the visual trail.
Color temperature.
Yeah. An open filter pushes the RGB values into searing whites and warm reds. As the musician closes the filter, the visualizer dynamically shifts the color palette in real time down into cool blues and dark cyans.
That is wild. And finally, we could visualize the acoustic space itself using CC91 and CC93, which govern reverb and chorus send levels.
Right, spatial mapping.
So high reverb values extend the decay calculations in the compute shader. A note played with a massive cathedral reverb will leave a visual trail that lingers on screen for seconds, bleeding into the notes around it.
While a dry, staccato bass synth with zero reverb will just vanish instantly, we are literally mapping acoustic space to screen space.
Okay, but when you layer all of these together, shimmering widths for vibrato, color temperature shifts for filters, horizontal drift for panning, and cascading releases for the sustained pedal, a logical question arises.
Is it too much?
Yeah. Does this display become an unreadable, chaotic mess? Is it simply too much sensory information for a user to process?
The psychology of human perception suggests otherwise, actually.
Really, it doesn't get overwhelming.
It doesn't become chaotic because the visual data is perfectly synchronized with the audio data the listener is processing. Our brains are remarkably adept at cross-modal association.
Cross-modal association.
Yeah. When your ear hears a note swell in volume and gain a harsh, bright filter edge, and your eye simultaneously sees a rectangle expand and shift from blue to red, your brain fuses those two inputs.
Ah, so it makes sense implicitly.
Exactly. It doesn't interpret the visual shift as random noise. It interprets it as a unified, truthful representation of a singular event. The visualizer basically stops being a graph and becomes an extension of the instrument itself.
That is a really profound realization. But, it all hinges on one massive assumption.
And we actually have the data.
Right. That we have access to this rich, expressive MIDI data in the first place.
Yeah.
What happens if the listener only has an MP3 file?
Yeah, that's the hurdle.
Or what if the MIDI file was just programmed click by click with a mouse and a sequencer, completely lacking any human expression, mod wheel data, or velocity dynamics?
This is where the modernization journey steps completely over the edge into the deep learning frontier.
Yes. Let's get into the AI.
Because if the data doesn't exist, we must extract the invisible truth directly from the audio waveform itself.
Okay, how do we do that?
The first step in moving from a reactive visualization system to an analytical one is audio pipeline integration. And that fundamentally relies on the fast Fourier transform, or FFT.
Okay, for those who might not be deep into signal processing, a fast Fourier transform is a mathematical algorithm that takes a complex audio signal, a waveform viewed over time, and breaks it apart into its constituent frequencies.
Right.
Think of it like tasting a really complex soup and being able to mathematically reverse engineer the exact milligram quantities of salt, pepper, garlic, and onion that went into it.
That is exactly what it does. The FFT takes a tiny slice of audio, maybe 20 milliseconds long, and splits it into discrete frequency bins.
And because the frequencies of musical notes are standardized we know that middle C oscillates at roughly 261.6 hertz.
We can look at the energy level in the specific FFT bin corresponding to that frequency.
So this completely replaces the reliance on a static MIDI velocity number.
Completely. We can derive the continuous acoustic energy of the note as it actually rings and decays in the physical room, and we drive our shader brightness directly from the audio physics.
But wait, an FFT applied to a mixed MP3 file gives you everything at once, right? The bass drum, the vocals, the guitars, the synths are all mashed together in those frequency bins.
Sure.
How do we retrieve the separation of our 16 columns? We can't just throw the whole messy mix at the screen.
That is where we implement source separation models. The architectural teardown points to highly advanced neural networks like DEMEX, developed by Meta's AI Research Lab, or Splitter by Deezer.
Okay, but how do those models actually isolate the instruments? They aren't just using simple EQ filters, are they?
Oh no, it's way beyond EQ. They utilize an architecture called a UNet, operating on spectrograms.
Spectrograms, let's define that.
A spectrogram is a visual representation of the audio, where the x-axis is time, the y-axis is frequency, and the brightness represents amplitude.
Got it.
The UNet neural network is trained on massive data sets of isolated stems like the raw vocal track by itself, the raw drum track by itself, paired with the final mixed song.
Okay, so it learns what they look like separately versus together.
Exactly. It learns the complex, intertwining visual patterns that a snare drum or a human voice makes on the spectrogram. When we feed it our live audio mix, the network generates highly precise mathematical masks.
Masks, like cutouts.
Yeah. It lays these masks over the spectrogram to isolate the specific patterns of the bass, drums, or melody, and then reconstructs the clean audio for each element in real time. We then feed these isolated audio streams in separate channels of our visualizer.
It is staggering that we can run that kind of AI inference in real time today.
It really is.
But even with isolated audio, we still need to know exactly when to trigger the visual rectangles. We need the note attacks.
Right, the onsets.
And
This requires automatic music transcription, or AMT.
AMT.
The current gold standard in the literature is a model architecture known as onsets and frames, which is heavily trained on a dataset called Maestro.
Maestro. What's in that data set?
Maestro contains hundreds of hours of virtuosic piano performances where the acoustic audio is perfectly, meticulously aligned with the raw MIDI data captured from the piano mechanisms.
So the model literally learns the exact acoustic signature of a physical hammer striking a string.
Yes. So instead of relying on a potentially laggy MIDI input, the AI just listens to the audio stream and predicts the exact onset of a note with millisecond precision. It knows exactly when the sound materialized in the physical room.
And it completely overcomes MIDI quantization lag, right?
Completely.
But the most theoretically complex aspect of this modernization, I think, is inferring the missing continuous controllers from an audio file.
Absolutely.
How do we retrieve CC data like pitch bends or expression swells from a flat MP3? I mean, the audio is just a wave.
For pitch, the process is algorithmic. We can use robust pitch tracking algorithms like YIN or its probabilistic variant, PYIN.
YNN and PYN.
Yeah. These algorithms use mathematical autocorrelation to track the fundamental frequency of an isolated audio signal.
So if a blues guitarist physically bends a string, pushing the note slightly sharp,
The PYN algorithm detects that microdeviation from the mathematical center of the pitch, and we can map that deviation directly to the visual pitch bend indicators at the bottom of our columns.
that handles pitch. But retrieving expression data like the mod wheel or the filter cutoff, that requires, as the document calls it, AI ghostwriting.
Ghostwriting, I love that term. The proposal outlines training transformer-based neural networks on vast databases of human performances.
A transformer model.
Yeah.
They excel at sequence-to-sequence prediction, right?
Exactly. It doesn't just look at a single frame of audio in isolation. It uses self-attention mechanisms to look at the entire context of a musical phrase. It analyzes the shape of the sound over time.
So if we train the transformer on thousands of hours of skilled synth performances, where both the raw audio and the actual MIDI controller data are known,
The AI learns the complex physical relationships. It analyzes the harmonic profile of a chord swelling over 3 seconds, and its attention mechanism recognizes the pattern.
and it deduces what a human would do.
Right. It deduces, based on my training, a human player would have moved the physical expression pedal exactly this much to achieve this specific acoustic swell.
That is crazy. It generates a synthetic mathematical curve representing that predicted movement.
Yes.
So, given a completely flat, expressionless audio recording, the AI effectively ghostwrites the missing human intent.
It synthesizes the mod wheel data, the filter cutoff data, the sustained pedal interactions, and feeds those predicted values directly into our WGPU compute shaders.
So the visualizer ceases to be a simple data plotter.
Exactly. It actively listens, analyzes, and infers the physical, muscular gestures of a human performer who might have recorded that track in a studio decades ago.
It literally resurrects the performance from the static audio.
It is beautiful.
It really is. It is taking the raw, constrained intent of a 1998 C program and fulfilling it using the absolute limits of modern technology.
Yeah,
We need to take a step back and just look at the trajectory we've covered today.
it's been a journey.
We started by unpacking a 16-bit application drawing simple colored rectangles on a CRT monitor, right? Fighting against segmented memory and CPU bottlenecks with the 1,000-event ring buffers.
And then we decoupled that monolithic architecture using Java and the JVM's concurrent thread management as a bridge to validate our logic without the friction of memory management.
Right. Then we threw out the CPU rendering entirely, descending to the metal with Rust.
Leveraging the web GPU standard to write WGSL compute shaders, transferring the calculation of 10,000 fading note trails to an army of parallel GPU cores.
We expanded the visual vocabulary, mapping the rich data of MIDI control change messages to shader parameters, translating sustain, expression, vibrato, and filter cutoffs into cascading releases, dynamic brightness, shimmering widths, and color temperature shifts.
And finally, we explored the deep learning frontier. We discussed how fast Fourier transforms, UNet source separation, automatic music transcription, and transformer-based AI can analyze a flat audio file to extract frequencies, isolate instruments, and ghostwrite the human expressiveness back into the visual pixels.
You know, the power of refactoring isn't just about updating syntax to run on modern machines. When you look at legacy code and old constraints through a modern architectural lens, you explode the possibilities of what the original tool can actually do.
Eric Ringel's 1998 source code was a phenomenal piece of engineering for its time. By leaving it accessible, it serves as an invitation to iterate, proving that the best way to understand the future of software is to thoroughly dissect its past.
I couldn't agree more. And I want to leave you with one final mind-bending thought based on everything we've unpacked today.
Ooh, what is it?
If a visualizer powered by compute shaders and neural networks becomes this accurate and this expressive-like, if it shows every subtle vibrato shimmer, every warm filter shift, and every acoustic decay in perfect real-time synchronization on a massive display,
Yeah.
how long until musicians start playing their instruments specifically to manipulate the visualizer?
Oh, wow. It creates a closed feedback loop between sight and sound.
Exactly. The tool built to reflect the music might eventually dictate how the music is performed. The musician plays the light.
That is something to chew on.
Keep exploring these strange architectural loops, keep digging into the source code of the things you use, and we will see you on the next deep dive.